So in the last video we discussed how if we know the strain within a material, uh, strains within a material, uh, we can then determine the stresses. Alright, and from those stresses we can then determine the factor of safety if we know the yield strength. Alright, so what we're going to talk about now is how we would experimentally measure these strains, epsilon x, epsilon y, and gamma xy, using these resistance strain gauges that we have here. Alright, so resistance strain gauges, there's two major types, metallic and semiconductors. Both of these have great spatial resolution, which means they can determine the strain at a specific point within a structure. Typically, they're unaffected by changes in temperature or other conditions, and they have very high frequency response, so they can measure dynamic loading. Strain gauges are quite old. They've been developed almost 90 years ago, 90 plus years ago at this point, and they're based off of the fact that the change in resistance in a wire is proportional to the change in length within the wire, or the strain within a wire. Okay, and resistance strain gauges are critical components that are used throughout many systems, specifically in load cells, pressure transducers, and torque sensors. Okay, so they're often used to measure things like loads, torques, and pressures. All right, so we're going to talk about the basics of metallic strain gauges and how metallic strain gauges works. Okay, so we know that the resistance within a wire is proportional to the density, the resistivity of the wire material, all right, and the length of the wire and the cross-sectional area. All right, so we can say that the change in resistance of that wire, all right, we can write in terms of these terms here. All right, all right. So if we can rewrite this term here in terms of the original resistance and the Poisson's ratio. So if we're going to just divide by the original resistance here, we end up getting the original length, the change in length, which is our strain, the Poisson's ratio, and the change in resistivity over over the original value of resistivity of the wire. So we can define this delta PE over PE term using something called the piezo resistance coefficient, which we denote here using the letter pi. Right? And all the piezo resistance coefficient means is it's the dependence of resistance due to mechanical strain. Right? So it's just another material property. Right? Of the metallic gauge. Okay? So we can rearrange the definition of the piezoelectric coefficient to determine the ratio of the change in resistivity over the original resistivity. Okay, so since we now know what this is, we can plug this value in to our original equation, and we can factor out the change in length over the original length. Right? So what we end up getting is that our change in resistance over resistance is proportional to the change in length over our length, which is the definition of an axial strain, all right, times the ratio of 1 plus 2 times the Poisson's ratio plus this piezo-resistive coefficient, which again is a material property, times, all right, the Young's modulus, which is another material property. So basically the change in resistance over the resistance is proportional to the strain within the material times a bunch of material properties of that material. Okay, so as long as you know what the material is in our metallic strain gauge, we can relate and we measure the change in resistance. We can then calculate our strain, which is what we're after. Okay, so in the next few videos, we'll talk about how you would solve the strain based off of that change in resistance measurement.